All right, we're going to look at problem 49 from 4.5 in the book here, the curve sketching section. And it's y equals the natural log of sine of x. Again, I'm calling it f of x. The function notation is kind of handy for labeling certain things, so I prefer to use it where I can. And the first thing I'm going to do is just think about the original function f of x here, and what do I know about it? So first of all, with the domain, are there any domain restrictions here? And with sine of x, there are no domain restrictions on the sine function, but there are domain restrictions for the natural log function. Natural log can only have the natural log of positive values, right? So that means that what's inside of that natural log, the sine of x, must be greater than 0 for the purposes of our domain here. So for the domain, I'm going to say, okay, sine of x has to be greater than 0. And if I picture on the unit circle, I'm looking at the values on the top half of the unit circle there, where the y coordinate is positive, because that's where the sine of x will be positive. And so my domain for f of x is going to be, 0 to pi, right? And then 2 pi to 3 pi. Also negative 2 pi to negative 1 pi. Basically, any even multiple of pi to any odd multiple, the next odd digit multiple of pi. So I'll show a couple examples here. Let's say negative 2 pi to negative pi. And I'm going to use parentheses here, because at the endpoints, at negative 2 pi and at negative pi, the sine of those values is equal to 0. And that means that the natural log, I'd be taking the natural log of 0, which is also undefined. So I'm going to do a union here, and we'll go from 0 to pi, union, 2 pi to 3 pi, and union. And we could do a dot, dot, dot on either side here. In fact, let me make a little room here. Now, there is maybe a more efficient way to write this too, but this is a valid way to give this set of intervals. Again, a cleaner, maybe more elegant way is to say, let's say k pi, comma, and then k plus 1 pi for basically any even integer k. Or I could say 2k pi, and then I can just say for any integer k. That might even be cleaner still. 2k plus 1 pi for all integers k. So that's a nicer way to say it. Good. So we got the domain. We're going to have these like intermittent pieces of this curve then, right? From any, like I said, any even integer multiple of pi to the next consecutive integer multiple of pi. And then, it'll be off. It'll be on again, off again through there. So we're going to focus on maybe one of these first. I think, because the thing is, the sine function, right, sine of x is periodic. And so when you go from 0 to pi, you're going to get these values as an output. Those are going to get plugged into the natural log function. And then the next time you go through from 2 pi to 3 pi, you're going to hit those same sine values that are going to get plugged into the natural log function again. So you're going to get the same output again. This whole thing is going to be a periodic function. Okay. We could do this without calculus too, because you can think, what kind of values are we getting here? We're going from 0 up until 1. And so what kind of values does the natural log give you when you go from 0 to 1? And you can probably guess what this is going to look like. But we're going to use some calculus here and do a little more than just that. All right, let's move on to the first derivative. And maybe we'll come back and look at this original function a little more. But, part of the reason I'm talking about this, I like to consider end behavior before we move on to the derivative. I like to look at things like the limit as x approaches infinity of f of x. And the problem is here, there is going to be no such limit, right? As x goes to infinity, we're going to keep going through this same cycle over and over and over again. And we're not going to zero in on any one value. There's not going to be a horizontal asymptote. Same with negative infinity here. So it's a good thing to take note of as well. It's also good to look for zeros of the function, actually, before we move on to the derivative. So let's say zeros of f of x. And, start on the outside and work your way in, right? Where does the natural log of something equal 0? And it's true that the natural log of 1 is 0, and that's really the only place, right? The natural log function is an increasing function. The graph of natural log of x looks kind of like that, and it crosses 0 at 1. So this function is only going to have a 0 when the inside of that logarithm is 1. In other words, where the sine of x equals 1. And that's going to happen repeatedly, right? It's going to happen at pi over 2. And then all the coterminal angles with pi over 2. So x equals pi over 2 plus 2k pi. Okay. So we got the zeros. Now we're ready to move on to the first derivative. Change colors here for our first derivative analysis. F prime of x is, the derivative of the natural log of x is, or the natural was 1 over x, right? So the natural log of stuff here, right? The natural log of a function of x is going to be 1 over that stuff, and then times the derivative of that stuff, which of course is going to be the cosine of x. And so, hey, that's the cotangent of x, isn't it? That's f prime. And we want to find kind of a sine chart for f prime of x here, for cotangent of x. That should be easy enough. Really, we really only need to look at the domain. So we're looking at these intervals 0 to pi, 2 pi to 3 pi, right? And it's going to be the same thing with cotangent as the cosine and sine in that it's going to repeat its values over those intervals. So if I just look at one of these from 0 to pi, I'm going to have the same thing occur as if I look from 2 pi to 3 pi. I don't need to do separate work for all of these. 4 pi to 5 pi, or better yet, how about 2k pi to 2k plus 1 pi for any integer k here. That's pretty much what this sine chart's going to do for me. And what I want to do is consider any zeros of the numerator or denominator here, right? So any places where cosine of x equals 0 or where sine of x equals 0. The sine of x equals 0 at those endpoints, right? At pi and at 0, at 2k plus 1 pi and at 2k pi. Cosine, so we already have those on there. Those are the endpoints of my interval. The cosine of x is going to equal 0 only at, right in between those, at pi over 2. Or again, for the general, it'll be 2k plus 1 pi and then plus another pi over 2. So I guess 2k plus 3 halves. 2k plus 1 half pi. How about that? That's enough. 2k plus pi over 2. Yeah, that'll do it. And 2k plus 1 half pi. Excuse me, that's not a good way to write it. 1 half parentheses. There we go. That's better. I was going to say that didn't seem right. All right. Anyway, the cotangent function. So again, if you think about on the unit circle, when you're looking from 0 to pi, the cosine is positive over here, but it's negative over here. The sine is positive on the entire interval. So when we're from 0 to pi over 2 on this part of the interval, both sine and cosine are positive, so we're going to get a positive ratio. Over here, though, from pi over 2 to pi, the cosine is negative, the sine's still positive. So that's what we're going to get. What that means is, since f prime is positive on the first part of this, each of these intervals of the domain here for the first half of each of these, and then negative for the second half, that means on each of those intervals, f is going to be increasing and then decreasing. And that means f is going to have relative maximums at all of those pi over 2 points. So f has a relative max for each x equals pi over 2 plus, again, 2k pi for all integers k. Because at those points, f prime is changing from positive to negative. Okay, and that's good. That's our first derivative analysis. We're going to look at the second derivative here. And for the second derivative, well, I just need the derivative of the cotangent function, right? And the derivative of cotangent is negative cosecant squared, okay, which is negative 1 over the sine squared of x. And so again, if I do a little sine chart here, and I really only care about from 0 to pi, if you picture the unit circle from 0 to pi, once again, the sign is always positive within that interval. And we're not including the endpoints, so I don't need to worry about that even. Those aren't in the domain. So if the sign's always positive, then negative 1 over the sine squared is going to always be negative. And so that means that these curves are all going to be concave down the whole way, right? The f function, when you graph it, each piece of it is going to be concave down. So f double prime is less than 0 for all x values in the domain of the function. And so f is concave down over its domain. All right, and I think we have enough information here to give a pretty decent graph of this function. One more thing maybe we should do is consider those maximum points that we found at pi over 2 plus 2k pi. Maybe we should find like the actual y value there. And you know what we already did, right? It's right here. Those are the zeros of f of x. If you plug those into the original function, which we already basically did, we solved for those as zeros, you'll see that the y value there is 0. So one more thing I'll just point out. You can kind of tell this anyway if you know that this is a maximum, right? These zeros of f of x are maximums, and they're on the x-axis, they're zeros. That tells us too that these pieces of the graph are all going to be below the x-axis, right? They're all going to be negative y values, except where they're 0. You can also tell that, again, from the original function. If you think the sine of x, the only outputs we're going to be looking at are from 0 to 1, right? Because where the sine of x was negative, it doesn't fit in the domain of the natural log function. And on the natural log graph, once again, the natural log graph from 0 to 1, it looks like that. Those are all negative values. So that's pretty much what we're looking at here. So when I graph this, if I just kind of look at below the x-axis here, here's the origin. And we're going to have values that as the sine of x gets close to 0, we're going to be looking at places where the natural log is, it's something approaching the natural log of 0. Those are all going to be vertical asymptotes, right? The natural log function has a vertical asymptote at x equals 0. So we're going to have vertical asymptotes anywhere that sine of x equals 0. I guess we could have talked about that before the derivatives. And so you can say that's going to occur at x equals, again, those endpoints of the domain, 0, pi, 2 pi, 3 pi, basically k pi for all integers k. So if we do 0 to pi, there's a vertical asymptote. There's one at 0, 2 pi. We'll go up to 3 pi just to see that iteration of this graph. And then, negative pi, negative 2 pi. And again, we have zeros, which are maximums at the pi over 2's plus 2k pi. So there's going to be one here. Whoops, I wanted to use a different color here. Pi over 2 at 2 pi plus pi over 2 and at negative 2 pi plus pi over 2. And those are maximums. We're going to be increasing up to those points from the vertical asymptote to that point, decreasing after. and concave down the whole way. And really, that's all we got to go on here. You're going to end up with a graph that looks like this. Which, again, you might have predicted without doing any of the calculus if you just kind of thought, again, about what that sine function does from 0 to pi. You know, it goes from a value of 0 to a value of 1 back to a value of 0. So the natural log of that has to go from approaching negative infinity up to a value of 1, because the natural log of 1 is, or sorry, up to a value of 0, because the natural log of 1 is 0, and then back toward that vertical asymptote of negative infinity as sine of x approaches 0 again, right? It's just going to keep doing that, right? And that's it. These periods in between here, those are gaps in the domain, so those are not part of the graph. And that's it.